graphing rational functions. So first we're going to look at a rational parent function. So the parent function for rationals is y is equal to 1 over x. So y is equal to 1 over x. This is also called a fraction. And for the parent function, the domain and range are going to be everything except 0. Because notice, since x is in the denominator, we can't divide by 0. So we have negative infinity to 0, union 0 with positive infinity. And that's going to be the same for the range. Then in rational functions, we have asymptotes. Asymptotes are boundaries that the function will approach but not touch or cross. So it will not touch or cross. There are two types of asymptotes. There's horizontal and vertical. For the parent function, the horizontal asymptote is y equals 0, and the vertical asymptote is x equals 0. This little note at the bottom tells us that if we have a function of any form a over x, with a being a number, then it's going to follow that these same asymptotes, domain and range of the parent function 1 over x. And what this means is, let's say you had 2 over x. Well, if you have 2 over x, it's going to follow the same domain and range, just like if you had 5 over x. So no matter what the number is on the numerator, as long as the denominator is just x, you're going to get the same things up here. Okay. We're going to look at two ways that we can graph rational functions. The first way is using the transformation form. And that transformation form is this equation here. The f of x is equal to a over x minus h plus k. Remember, when we used h and k in previous units, that represent the vertex. Well, we no longer are representing h and k as the vertex, but instead as values that help us determine the vertical and horizontal asymptote. For example, the vertical asymptote is going to be x is equal to h. Or another way you could view this is whatever the denominator is, so in this case, x minus h, if we set that equal to 0 and solve for x, we get x equals h. The horizontal asymptote is going to be y equals k, so it's whatever number is on the outside of that fraction. And then if a is negative, there's a reflection over the x-axis, just like any of the other attributes we learned before. Okay. It's important to note that the h value in this transformation form shifts left to right. The k value shifts up and down. And then again, a tells us if we have a reflection or not. So let's look at example 1. And another way we know that we are using this type, the transformation form, is that we are not able to factor the denominator. So looking at this denominator here, x plus 1, we notice that this is not factorable. We can't simplify this any further. Since it's not factorable, we know we're using that transformation form, which is the y is equal to a over x minus h plus k. However, in order to put it in this form, we have to use long division. So our equation here, g of x is equal to 3x plus 5 over x plus 1. We're going to rewrite this in long division where we have x plus 1 on the outside dividing into 3x plus 5. Now remember, during long division, what we're doing is we're looking at the first term of each one. So we're looking at the x and the 3x. And we're asking ourselves, how many times can the x go into 3x? Well, it can go in 3 times. And then we're going to take that 3 and multiply it by everything on the outside. So we have 3 times x, which is 3x. 3 times 1 is 3. And then from here, we change our signs and we add down. So 3x minus 3x cancels. And 5 minus 3 gives us 2. So that means we have g of x is equal to 2 over x plus 1 plus 3. We write it this way so it looks exactly like our transformation form. Okay. So here we can see that our k value is 3. Our h value is x plus 1 equals 0, which means it's negative 1. And our a value is 2, which means it's positive. Okay. Knowing all this helps us find our vertical and horizontal asymptotes based on that h and k. So for our horizontal asymptote, we have y is equal to k, which means we have y is equal to 3. And again, that is our horizontal asymptote. And then for the vertical one, we have x is equal to h, so x is equal to negative 1, which is our vertical asymptote. And actually what I'm going to do is change the color so you can see it color-coded on the graph. So first, the horizontal asymptote, y equals 3. We go to the y's, we find the 3, and we do a dashed horizontal line. For the vertical asymptote, we find negative 1 on the x's, and then we do a dashed vertical line. Since our a value is positive, we know that there's not going to be a reflection, so it's going to look similar to our parent function above. And notice in this parent function over here, we had our two graphs going on the top right and the bottom left. So that's where we're going to draw our graphs here. Okay, so on the top right, bottom left. And it doesn't have to be exact, this is just a sketch. Okay, number 2, we're going to do the same thing. We first look at the denominator. Okay, it's not factorable, so we have to do long division. So I have x plus 4 dividing into 2x plus 4. X can go into 2x 2 times, so I'm left with 2x plus 8. Change the signs, the x's cancel out, and I'm left with negative 4. So that means I have g of x is equal to negative 4 over x plus 4 plus 2, where k is equal to 2, which means that this is my horizontal asymptote y equals 2. And then h is equal to x plus 4 equals 0, which is x equal to negative 4, which is my vertical asymptote. And then my a value is negative 4, and since it's negative, I know I'm going to have a reflection over the x-axis. Okay, so taking all of these, my horizontal asymptote at y equals 2 is going to be a dashed horizontal line at 2. And then x equals negative 4, it's going to be a dashed vertical line for my vertical asymptote. But since I have a reflection, no longer is my graph going to be in the top right, bottom left. It's now going to be on the opposite. It's now going to be on the top left, bottom right. So I would draw the graph like this. And that's our answer. Okay, number 3 is a little tricky because when we are doing the long division here, so I'm going to write it 2x plus 1 going into 3x minus 1. If you think to yourself, how many times did 2x go into 3x? You want to say 1 because 2 can only go into 3 one time. However, we want it to go in exactly. So in order to do that, our answer is going to include a fraction. So what can I multiply 2 by to get 3? Well, I can multiply 2 by 3 halves, and I get 3. So this is 3x plus 3 halves. Change the signs. The x's cancel out, and I am left with negative 1 minus 3 halves. Well, negative 1 minus 3 halves tells me I need to get a common denominator, which would be 2. So instead of negative 1, this is actually the same as saying negative 2 over 2. So negative 2 over 2 minus 3 over 2 gives me negative 5 over 2. So I have f of x is equal to negative 5 halves over 2x plus 1 plus 3 halves, which means my k value is 3 halves. So I have y is equal to 3 halves. And then my h value is that 2x plus 1 equals 0, which means I have x is equal to negative 1 half. And my a value is negative 5 halves, and since it's negative, this is going to be a reflection over the x-axis. Okay, and just remember this is vertical and this is horizontal. So using that information, I'm now going to graph it. So I have my horizontal asymptote at y equals 3 halves, which is about 1.5. And then I have my vertical asymptote at x equals negative 1 half, so right before the negative 1. And since it's a reflection, I know it's going to be in the opposite areas. Okay. Now for the second part of the notes. So this is graphing rational functions that are not in that transformation form. So for the most part, everything looks kind of similar. But now, in order to find vertical asymptotes, we have to remember that we cannot divide by 0. So that means when we look at our denominators now, they're going to be factorable. So in order to find that vertical asymptote, we're going to have to first factor the denominator, set it equal to 0, and solve. And then whatever numbers we get, those are our vertical asymptotes. For the horizontal asymptotes, we have to look at the exponents. Okay, horizontal asymptotes, think exponents. So if we have exponents that are different, so notice in this example it says lower exponent over higher exponent, then we know that our horizontal asymptote has to be y equals 0. So think of this example. Let's say we have the example of 5x squared over 3x to the 4th. Okay. We have an exponent of 2 on the top, but an exponent of 4 on the bottom. They're different, and since they're different, we know it's going to be y equals 0 for the horizontal asymptote. Okay. That's one case, case 1. In case 2, let's say that both of our exponents are the same. So let's have our same example here, but now we have 5x squared over 3x squared. Notice that these two exponents are the same. So instead, if they're the same, we only look at the leading coefficients of both of them. And remember, the leading coefficient is the number in front of x. So for the numerator, that is 5, and for the denominator, that is 3. So this would give us y is equal to 5 over 3 as our horizontal asymptote. Lastly, since we are able to factor, that means there's a possibility that something can cancel. This point where something can cancel is called a removable discontinuity. So in order to find that, we would factor both the numerator and denominator if that's possible. So factor the numerator and denominator. If anything cancels, then we have a removable discontinuity at the point x comma y. So that means you would take your x value that you found from the part that canceled out. You would set that equal to 0, find your x, plug it back into the simplified equation to find y. This is going to create a hole in our graph. Okay, so let's look at this example here. Okay, let's say we already factored the numerator and we got x plus 3 times x plus 2. And then we already factored the denominator and we got x plus 3 over x plus 7. Okay. Notice right away that this x plus 3 can cancel out. Since it cancels out, we know that there is a removable discontinuity, a hole in the graph. So from here, we're going to take the value that we crossed out, so x plus 3, set it equal to 0, and we get x is equal to -3. But remember, it's a point, so in order to find that point, we're going to take that -3 and we're going to plug it into the part that is simplified, so without the part that we canceled out. So we have x plus 2 over x plus 7. I'm going to plug in a -3, so -3 plus 2 over -3 plus 7. This gives us -1 over 4, which means we have the discontinuity point of -3, -1/4. Okay, this is the hole in the graph. And so if we were to graph this, -3, -1/4 would be like somewhere over here. We would be drawing our graph where it looks like there is a gap in the function. So now let's look at some examples. Okay. Example 4 says sketch the graph for f of x is equal to x plus 4 over 4x minus 16. Notice here, this denominator, we can factor. We can factor this by taking out a GCF of 4, so we're left with x plus 4 over 4 times x minus 4. Okay. Because we can factor this, that is why we do this method and not the long division like before. Then we check if anything can cancel. So since nothing can cancel, that means we do not have a removable discontinuity, so we would just put none. And then for the vertical asymptotes, remember we have to take the denominator and set it equal to 0. Well, the denominator is 4 times x minus 4, set that equal to 0. 4 equals 0 doesn't make sense, so we skip it, and x minus 4 equals 0 gives us x equals 4. That is our vertical asymptote. For the horizontal asymptote, we have to look at the exponents. So going back up here, notice that the x's here are single x's. They do not have an exponent, so we assume that exponent is 1. And since they're exactly the same, we look at the leading coefficients in front of the x's. Well, in front of this x, there isn't anything, so we assume it's 1. And in front of the other x is 4, meaning we would look at 1/4. So that means our horizontal asymptote for this one is y is equal to 1/4. And then in order to find our y-intercept, we have to plug in 0 for x. So I have 0 plus 4 over 4 times 0 minus 16. So I have 4 over -16, which is equal to -1/4. So my y-intercept is 0, -1/4. And we're going to do that every time. Okay, then for our domain and range, remember, for the domain, we have to take into account the vertical asymptote, and for the range, the horizontal asymptote. So if we were writing this out, it's always going to be -infinity, vertical asymptote, union vertical asymptote, +infinity, versus -infinity, horizontal asymptote, union horizontal asymptote, +infinity. So in our case, it's going to be -infinity to 4, union 4 to +infinity, and -infinity to 1/4, union 1/4 to +infinity. Okay. Then from here, I can graph my horizontal and vertical asymptotes and then figure out my graph. So I have x is equal to 4, and then I have y is equal to 1/4. My original function, since my leading coefficient was 1 and it's positive, I'm not going to have a reflection. So my graph is going to look like this. Number 5, I have g of x is equal to -4 over x squared minus 3. Notice here that I can factor this by taking out an x. So I'm left with negative 4 over x times x minus 3. I can't cancel anything out, so I do not have any removable discontinuities. And my vertical asymptote is the denominator set equal to 0. So x times x minus 3 equals 0. Implies that I now have two vertical asymptotes, one at x equals 0 and the other at x minus 3 equals 0, which is x equals 3. My horizontal asymptotes, I look back at my exponents and notice the numerator does not have an exponent at all, so we can assume it's 0, but the denominator has an exponent of 2, so that means they're different, which means my horizontal asymptote is y equals 0. For my y-intercept, I have to plug in 0 for x, so I have negative 4 over 0 squared minus 3 times 0, which gives me negative 4 over 0, which is undefined. Remember, I cannot divide by 0, so that tells me I do not have a y-intercept. Looking at the domain, remember my domain is affected by my vertical asymptotes. Since I have two vertical asymptotes this time, a 0 and a 3, I'm going to have a third interval with another union. So this is negative infinity to 0, union 0 to 3, union 3 to infinity. And then my range is just not including the 0. So negative infinity to 0, union 0 to infinity. Okay, so if I was to graph this, my vertical asymptotes at 0 and 3, and then I have x is equal to 3, and then I have a horizontal asymptote at y equals 0. And so in order to graph this, I first have to look at my original function. Since my original function has a negative 4 in the numerator, this tells me that I'm going to have a reflection over the x-axis. And since I'm going to have a reflection over the x-axis, no longer is my graph going to look like it's going up. It's going to look like majority of it is going down. So I'm going to have a function here in between these two asymptotes, and then a function on either end going in opposite directions. Number 6, before I begin, this one does have a typo, so this should be x squared plus x minus 6. Notice that the numerator and the denominator can be factored. So in order to factor this, I'm just going to use the AC method. So the first one, two numbers that multiply to negative 6 but add to positive 1. This would be 3 and negative 2, so x plus 3 over x minus 2. And then on the bottom, two numbers that multiply to 3 but add to 4 would be x plus 3 times x plus 1. Notice after I factor these that I see that the x plus 3's can cancel out, which means I do have a removable discontinuity at x plus 3 equals 0, which means I have x is equal to negative 3. I'm then going to plug in that negative 3 into the remainder x minus 2 over x plus 1, which gives me negative 3 minus 2 over negative 3 plus 1, which gives me negative 5 over negative 2, which is 5 over 2. So that means I have the discontinuity point at negative 3 5/2. Okay. My vertical asymptote is my denominator set equal to 0, but I only look at the simplified part. So I only have x plus 1 left, so this is x plus 1 equals 0, which means I have x is equal to negative 1. And then my horizontal asymptotes, since both of the exponents are 2, they're exactly the same. So I look at the numbers in front of them, and in front of both is 1, so we have y is equal to 1. For the y-intercept, I plug in 0 for x, so I have 0 squared plus 0 minus 6 over 0 squared plus 4 times 0 plus 3. This gives me negative 6 over 3, which is negative 2. So I have 0, negative 2 as my y-intercept. For my domain, I have negative infinity to negative 1, union negative 1 to positive infinity. And then range, negative infinity to 1, union 1 to positive infinity. And since my original function is positive, it's not going to have a reflection. So graphing this, I have my vertical asymptote here and my horizontal asymptote here. And then my function going as normal, just like the parent function, because I do not have a negative a value. Number 7, notice that both the numerator and the denominator can be factored. I'm going to factor this real quick. And remember, I'm just using the AC method. So I have x minus 10 times x minus 2 over x minus 2 times x plus 2. Notice that my x minus 2's will cancel out. So I have a removable discontinuity at x minus 2 equals 0, which means x is equal to 2. So I'm going to plug in that 2 into whatever is left over. So x minus 10 over x plus 2. This gives me 2 minus 10 over 2 plus 2, which is negative 8 over 4, which is negative 2. So I have the point 2, negative 2 for my discontinuity, my removable discontinuity. For my vertical asymptote, I'm going to look at the denominator and see what's left. So I have x plus 2, set that equal to 0, x is equal to negative 2. For my horizontal asymptote, notice that my x squared and x squared, they're both the same. So I'm going to look at the coefficients in the front. Since they're both 1, I have y is equal to 1. For my y-intercept, I'm going to plug in 0 for x. So I have 0 squared minus 12 times 0 plus 20 over 0 squared minus 4. This gives me 20 over negative 4, which is negative 5. So I have the point 0 comma negative 5. And then for my domain, I have negative infinity comma negative 2, union negative 2 to infinity. And then negative infinity to 1, union 1 to infinity. Okay, so plotting my asymptotes of negative 2, my vertical one at negative 2, and my horizontal one at 1, I do not have any reflections, so I'm just going to do my graph as normal. Okay, and then last one, number 8. We have f of x is equal to x minus 8 over x squared minus 6x minus 16. Well, I can simplify this to x minus 8 over x minus 8 times x plus 2. Notice how I can cancel out the x minus 8's, which means I have a removable discontinuity at x minus 8 equals 0, which means that x is equal to 8. And I'm going to plug that back into what's left over, which is 1 over x plus 2. And I get 1 over 8 plus 2, which is 1/10. So I have the point 8 comma 1/10. My vertical asymptote is whatever is left over in the domain set equal to 0. So x plus 2 equals 0 means x is equal to negative 2. My horizontal asymptote, since my exponents are different from the numerator and the denominator, I have y is equal to 0. My y-intercept, I'm going to plug in 0 for x, so I get 0 minus 8 over 0 squared minus 6 times 0 minus 16. This gives me negative 8 over negative 16, which is positive 1/2, so I have the point 0 1/2. And for the domain, I have negative infinity to negative 2, union negative 2 to positive infinity. And for the range, I have negative infinity to 0, union 0 to infinity. And since my original function is positive, I'm not going to have a reflection. So I'm going to go ahead and graph those vertical asymptotes at x equals negative 2, and the horizontal one at y is equal to 0. And I forgot to do these before, but I want to show you how the removable discontinuity looks. So I'm going to go ahead and plot that hole at 8 comma 1/10, which is right here. And then I'm going to plot the y-intercept at 0 1/2, which is right here. So what that means is that my function is going to look like it's crossing through this, but where the removable discontinuity is, there is going to be a hole in the graph. So right here, that hole is the removable discontinuity, which means that point does not exist on this rational function.